So I'd like to thank the organizer for the invitation. It's a pleasure to be here. So I'm going to talk about information inequalities and especially the notion of dual. So first I will try to explain why we study inequalities, just quickly, and then try to explain which notion, what do I mean by dual. So why do we study information inequalities is to study the entropic region. So just to make things clear, so we have, for instance, if we have x1 to xn that are random variables, then we want to study the entropy, all the possible entropies and joint entropies. So the entropy of x1, the entropy of x1 and x2 jointly, and until the entropy of the whole tuple. So whenever we have some random variables, we can study this. We can look at this vector, which belongs to r to the 2 to the n minus 1. We have 2 to the n minus 1 possible entropies. So we have a point in. So it's an object. Its closure is convex. We know some properties. And what we want to do with information inequalities is to look at how to define this object using inequalities. So, for instance, this could be some inequalities. Inequality is just some subspace that says, okay, all of the object is on this side. So this is how we see inequalities. So, okay, I don't have to tell you why they are really important. So, but I can. So, how we will define inequalities? It will just be some coefficient Cj, where J is just a subset of the indices. So for each possible entropy tuple, I associate some coefficient Cj, and now I call this an inequality if for all possible random variables, this inequality holds. That is the sum of Cj times entropy of Xj is always non-negative. So this is what I will call a linear information inequality. Okay. So what has been studied is linear information inequalities, but not only for entropy, but also for vector subspaces, and also it's related to polymatroids. So, okay, actually there are some things that are related. Polymatroids, entropic points, and let's say vector subspaces. And for these objects, we will study the following quantity. So, of course, for entropic points, I said it's the entropy. This is our main object. Then for polymatroids, we can view them as a rank function. And vector subspaces, we will study the dimension. So, for instance, for vector subspaces, we call them rank inequalities. Okay. Okay, now what I will need is I will need one definition. It's the definition for balanced inequalities. So what's a balanced inequality? It's just when you have such an inequality, we say that it's balanced if the sum of coefficients of all coefficients that involve, for example, variable I. So we take we take all possible variables. So we have x1, x2, xn. Then we look at, for this particular variable, the sum of all the coefficients for which it is involved in the inequality. So if, for instance, if we have, for the mutual information between A and B, this is an inequality. This is just entropy of A plus entropy of B minus entropy of AB. Okay. So here the coefficients are one for A, one for B, and -1 for AB. So we say that an inequality is balanced if this coefficient, the coefficient involving, for instance, here only A is 0. So that here this is balanced. Why? Because the sum of coefficient for A is +1 and -1. Okay. In terms of information diagrams, for instance, for instance for 3 random variables, it just means that if we look at, sorry. I don't see why do you mean the size of J? So here,
1 + 1 - 2.
Okay, so here, because A is, okay, I just say that A is involved in here and here. So in my definition, I just mean that, okay. So, okay, if you have no idea what it does, it just says that we can always assume that these parts are 0. It means that we don't have any private information. Because when we look at the balanced inequality, it doesn't put any weight on these parts. Okay. So what I'd like to do is just tell you how why I want to study the dual and which dual. So just to cut the suspense, it's just the dual for matroids and polymatroids. So if we look at polymatroids, we see that we have some basic operations. For instance, if we have two polymatroids, we can take the sum and any linear combination, and it will stay a polymatroid. We have an operation called the deletion, where we just focused on some part of the ground set, and we have another operation which is called contraction. So okay, this we can just say that. For deletion, when we have so if we have two polymatroids, f1, f2, and we take the sum, then this function f is still a polymatroid. For deletion, if we have some polymatroid f, we can restrict it to a subset M, and obviously it will stay a polymatroid. For contraction, it's not so clear. So the definition of contraction, so you contract. It's a set K, a subset K, and then you take this formula to be the contraction, and you can see take some time, but you can see that it's also a polymatroid. Sometimes I like to call this f of J given K. Okay. What I like about this operation is that they somehow have a counterpart in for entropic points and for vector subspaces. For instance, the sum, you just take independent copies of. So if you have okay, if you have two sets of random variables, so two entropic vectors, you can take the take the sum of these two vectors. And how to implement the sum? You just take two independent copies of the original two sets of random variables, and magically the entropy will just be the sum. And with some more work, you can also do some any linear combination. For deletion, this is trivial. For contraction, it says that whenever we have some random variables, then we can construct a new. Okay, maybe I can write it down. So if we have x1 up to xn, then we can find y1 up to, I don't know, n minus k, such that the entropy of yj is just the conditional exactly the conditional entropy for x. So this is the contraction for polymatroids, and I claim that I can find some random variable yi up to yn minus k, such that their entropy is exactly or close to the entropy of xj given xk. And this is done just by actually you can achieve this only for almost entropic points. So you can achieve you might not achieve equality exactly, but in the limit you will achieve equality. So I'm given x. So I'm given I'm given the all of the I'm given entropies for x and even the random variables, and I want to find new random variables yi, such that their entropy is the conditional entropy of xj given xk. So somehow I want to extract a part of the entropy of x, but conditional to some other. So k is fixed here. So you always take a condition. You always condition to the same subset of random variables, and you want to find some distribution that such that the entropy is exactly this conditional entropy.
So my question is, you are applying something beyond like looking at this conditional random variable. So I can look at this conditional distribution. Of course, it's a random variable. It has a certain entropy. Okay, if you look at this, you cannot define a single distribution, because this will define actually several distributions for all possible values of xk. So somehow you have to combine this conditional distribution to make them into a new random variables, etc. So it's not as straightforward as. Yeah, exactly. So it's nothing too difficult, but it's not that trivial. So I'm just saying that, okay, we have this operation, and we have some counterpart for entropy. And somehow there's, okay, we have probably convolutions also, but this Matouche has already talked about. And what I want to talk about is dual. And for the dual, I don't want to mess up the formula. So whenever I have some f, that is a polymatroid, I can define its dual by, so I put a star.
Okay, so the dual for the dual of f is just f of the complement of j minus f of j plus the sum of all of the rank function of all possible singleton that is in j. So this actually, this is the standard notion if you look at the dual for a matroid and you replace h by the rank function of a matroid. This is the only definition of a dual for a matroid. So for polymatroids, this is the it's not the definition, but it's a definition that is independent, I think, of the particular polymatroid. And takes more work to show that it's actually a polymatroid, but it is. And I don't want to get too technical. Not so much. I mean, it's not apparent. I mean, you can rewrite this as if I use this. I mean, just say that. So somehow you take minus the rank of the original thing, but conditional to all of the rest, plus this. But
can you explain the meaning of this? I think at least it's a very simple case. For example, if n equals 2 and g consists of 2 elements.
Probably, yeah. I will show some example in the rest of the talk. Okay. Yeah, probably it will come. Okay, maybe I can say that. Okay, if we have three, so this particular information triple, which is just the XOR of let's say two random variable a and b, and you take a XOR b. If you take the dual, then it will look like this: zeros almost everywhere, and n. So somehow the XOR gets maps to variables that are all equal. So it kind of reverses the how to say. Yeah. So as Matouche said, nobody understands duality. Okay, so obviously we want to find, we would like to find a counterpart of dual for polymatroids to vector spaces or entropic points. So
Yes.
Okay.
That's the only case where
Okay, I've never studied in Gaussian, so probably I will talk to you after.
Well, what happens if you put J to be the empty set? I'm not seeing the get 0.
If J is the empty set, good question.
Looks like you get n of n, not 0.
Did I do something wrong?
So would you agree?
Yeah,
The question is the formula correct? Because it doesn't
yeah. Maybe I mixed. Let me check. Let me check because So I think this formula works. Wait.
Second term should be Fn.
Yeah. Actually, yeah. Yeah. So then it should be. No, actually, yeah. Sorry. Let me check. Yeah.
The duality is well understood in the linear setting. You take linear code, and put uniform distribution into entropy, and this is correct. Then you take dual code, and that it gives you that formula.
So you're just looking for the rank of the dual network. Or you don't need this. Means that if you know the rank function of the dual network, you just get this.
Yeah.
So that's it.
Okay. Thanks. Okay. So. So what I want to do is, what I try to do is to find a counterpart for entropic points. And somehow I had to shift my view from entropic points to information inequalities. So first, so I want to say that this thing has been studied, so probably it's not. So what I claim is probably nobody understands duality, but for entropic points, and of course it's somehow known for in other cases, right? And I think so. It was. I was inspired by a question by Ferro Matouche that has he has a result on semi-matroid, I think, which says that if you have a particular semi-matroid and want to implement it into an entropic point, and now you take his dual, and somehow the dual is not entropic. So you have an entropic semi-matroid, whose dual is not entropic. The question is, could it be also almost entropic? So this wasn't answered yet. Okay. So what I want to define is some dual, let's say, operator that, for instance, will take some inequality. And will transform it into, by definition, that will act linearly on this inequality, and will transform it into H star of xj. So whenever I have some inequality, I will just define its dual by taking the dual of every entropy term. And by the dual of entropy term is just this dual. I will replace f by h. Sorry. Okay. Okay. So, okay. First thing that I want to say is that I will try to focus on balanced inequalities. Why balanced inequalities? Because we can notice that whenever we have an inequality and we take its dual, then the dual is balanced. Why is balanced? Because when you look at this definition, then you can see that it will satisfy this inequality, this equality. So whenever I have a variable that is involved in any whenever I have a variable, then because of this formula, automatically the coefficients that involve a single random variable will cancel. Okay.
So, and why do I call this dual? Because whenever I have some inequality I, then I take twice the dual, then it's not exactly I, but it's the balanced version of I. So somehow the dual, taking twice the dual almost keeps the same inequalities. So, okay. Okay, now I want to see what, I want to show you what duality does for polymatroids. But I will show you, I will write it in the language of entropy. So what I want to say is that what happens for Shannon-type inequalities. So, okay. Shannon-type inequalities, the basic Shannon inequality is the mutual information between A and B given C is non-negative. Now, if I take the dual of this, will I get an inequality? So before I do anything, just I have to take care of, I have to say something. When you take the dual, it's always, this operator is also, it depends on the number of variables in some way. So, okay. I will show you by saying that, okay, now, because it looks like we have 3 random variables, but we could have many others. So let's say instead of having only ABC, we have ABCD. So that you can see, you will see how it works. So I can rewrite this as, just by expanding, this is entropy of AC plus entropy of BC minus entropy of ABC minus entropy of C. And I take the dual of this. So it just means taking the dual of everything inside. So for AC, we get minus h of AC given the complement of AC, which is BD, plus h of A plus h of C. For BC, we get almost the same thing, so h of BC given AD plus h of B plus h of C. For ABC, we get ABC given D minus the entropy of these 3 things. And for h of C, h star of C, we get C given ABD minus h of C. And magically, all of these terms cancel. Here, I can rewrite it of entropy of ABCD minus BD. And for the 4 terms, I have twice, minus 2 times entropy of ABCD. Here I have plus 2 entropy of ABCD, so it cancels. So all I get is actually BD plus AD minus D minus ABD, which is just the mutual information between A and B given D. Sorry? Yeah. Thanks. Conclusion, Shannon-type inequalities are stable under duality. Why? Because Shannon-type inequalities are just linear combination of those with possibly other instances of the random variables. So, okay. So this is a good thing. So now I want to check, I want to go to vector spaces. So for vector spaces, so Randall told the story, so up to 3 random variables, it's almost the same story. It's the same inequalities as, so all of these inequalities are the same. Up to n equals 4, then something happens, is that we get a new inequality, which is called Ingleton inequality.
which looks like this. So this is an instance of the basic inequality. So we already know that duality is linear operator because I defined so. And we know that conditional things just get mapped to something like this. So if you believe me, this will translate into, wow. So for mutual information, it's just the same, but now the condition is just everything else. So here we have 4 random variables A, B, C, D. So here it will be D because I just put, it's just A, B, but given everything else that's not here. This doesn't look like anything, but actually if you write it, you will get something like this. Which is just Ingleton inequality, but on another side of the cone. So in some sense, Ingleton inequality is self-dual.
So how do you get it?
By rewriting. I mean, you have to explain everything. So you just. Yeah. Yeah.
So as long as you have in your definition of the dual, you have a way of defining the dual, then the inequalities.
Yeah. So apparently we have experts that are saying that everything I do here is just normal, which is true because actually what happens for rank inequalities is that you can take the orthogonal complement of the vector spaces, and then you can define a proper dual for vector spaces. So actually this is not so surprising. But actually, do anyone have a reference about this that says that you can take the how to define, so who defined the dual for vector spaces exactly in this setting, that you can take the orthogonal complement? So if anybody knows, please tell me a reference. So this, as Babak says, rank inequalities are stable by dual. So for instance, for n equals 5, the paper by DF said just tells us that there are 24 new non-Ingletonian inequalities. So we have, when we have 5 random, 5 vector subspaces, we have Shannon-type inequalities, Ingleton inequalities, plus 24 new inequalities that we didn't know before. And duality just gets them to 13 inequalities because some of them are dual to each other, some are self-dual. So maybe it's a way to, I don't know, symmetrize more the problem and gain some. Okay. So, okay, now, what happens for non-Shannon-type inequalities? So we have this inequality, which looks like Ingleton. But then we had some terms. And this is a non-Shannon-type inequality. And I think it was even in the slide of Laszlo last week. So I think it's the inequality that was first in Makarychev, Romashenko, Vereshchagin paper. So it's a 5-variable inequality, and
when you take the dual, you get some kind of thing that looks like Ingleton, but so it's Ingleton, but with a new condition E. Okay, let me check. Okay, I will drop just to E plus. So at first, I thought that this inequality was reasonable, and maybe it's a valid inequality, but it turns out that it's not valid. And I found some counterexample that says that, so I find a 5-tuple of random variable A, B, C, E, such that this, so it's parameterized by epsilon, so such that this is theta of epsilon, this is theta epsilon square, and everything else is 0. So meaning that this inequality cannot be true. And obviously not true because both parts can be made as larger. So I have the example. It's just so it's so it's actually binary, and out of the 32 possible items, it has only 8. And so it just says that now, what's the big picture? We have, let's say, the cone for Shannon inequalities, which is the outer bound. We have an inner bound that is rank inequalities. And somehow the entropy cone is like this. And we have this 5-variable inequality that when we dualize it, makes something like this. And I found the point here that says, okay, this inequality cannot be true. So somehow, we have defined a cone that is not stable by duality inside 2 cones that are stable by duality. So, okay. So notice that this is for 5 random variables, and what happens for 4, I have no idea. So it could be that the cone of entropic points for 4 random variables is still stable by dual. And this will imply some symmetry on your work. Okay, and quickly I would just want to mention something. Some possible application to secret sharing and to any information theoretic problem, like network coding, index coding, distributive storage.
If you want to show the distribution itself, or if you thought it is not too difficult.
So secret sharing. Yeah, I know you don't believe me, but okay. For secret sharing, what's secret sharing? We have some variable that is a secret that we will call S, and we have a set P of participants. We have n participants that will be given some information, and we want that some groups get to recover the secret, and some other groups know nothing about the secret. So this means that, okay, let's say that A is authorized, meaning A can get the secret. Then this can be modeled as the mutual information between S, the secret, and the set, and the subset, is the entropy of S. So saying that A knows S, actually. So when you dualize this, I will spare the computation, but we get something like, what do we get? We get the information between S and P minus A, so the complement of A is 0. So meaning that the set P minus A should not get any information on S. So P minus A is a forbidden set. And vice versa, if we have a B that is forbidden, then by some computation, we'll get that P minus B is authorized. So
You're given the authorized and forbidden sets to sort of parameter.
So what I'm given is a secret sharing problem. I have some sets are authorized, some sets are forbidden.
And that's all sets are specified as one or the other, or you don't care?
All sets are specified. I mean, this is, if all sets are specified, then this is called perfect secret sharing, but I mean, it's just one example. What's nice about this example is that in secret sharing, we can define, so if we have the set of all possible things that are authorized, this is called an access structure. And we can actually take the dual of an access structure, and by defining the dual like this, it will actually define the dual secret sharing problem for the dual access structure. So somehow taking the dual for the secret sharing requirements maps to another secret sharing problem, which is the secret sharing problem for the dual of the access structure. This probably is not the case for network coding, but maybe network coding, it maps to some other, maybe index coding problem or some, so it's not clear that for any instance of a problem, it will map, the dual will map to another instance of the same problem. But still, I mean, this is something interesting.
Is there a limit on the size of the sets?
So, I mean,
They're not necessarily the same, the authorized sets, or?
so here I just assume that we have n participants and we can get, and we have any access structure. So of course the access structure should have some, so first it should be monotone, and so it has some particular structure actually. So it's not, so for instance, if a set has a secret, then any superset should also have the secret. So this is just basic secret sharing. So what I'm saying is that I can define some dual for secret sharing, a secret sharing problem, but then I can study it using, so the bound for secret sharing were found using information inequalities. So what I'm trying to do is, so it's actually an open question. Can we, one of the biggest open question in secret sharing is the best possible scheme for an access structure almost the same as the best possible scheme for the dual access structure? And this might be a way to show that it is not. So it's still open. But it might prove some separation between one problem and its dual. And I'm done.